But that's not what's actually going on. If it were like that, it would just be like the Pastafarian theory that says global temperatures have gone up and piracy has gone down, therefore we need more piracy. But the difference between the piracy theory of global warming and what real climate science is doing is that real climate science has got a mechanism. And the mechanism was recognized in 1827 and measured in 1860. And there's still uncertainties about all the feedbacks in the system, but they also make predictions that are far more complicated than just referring to a single number. It isn't all about a single global number, the temperature of the planet. In 1975 already, computer models were made that modeled the Earth as a two-dimensional object with a height of an atmosphere and a latitude replicated around the axis. So this is showing latitude and height. And they made predictions not just of a single global warming, but how much warming do you get everywhere when you look in different locations, look at radiative transfer using the known equations of physics, with heat flowing in at the equator and out at the poles. And these computer models made detailed predictions, more than just one number. These are the predictions if carbon dioxide concentrations were doubled. And the predictions include details like you get warming in the troposphere, near ground level, and you get cooling in the stratosphere. Plus, you get more warming at the poles than you get at medium latitudes. So the predictions are detailed, and they're testable, as long as humanity does the right thing and carries on emitting carbon dioxide so we can see what happens. And humanity's been doing a reasonable job. We haven't doubled carbon dioxide concentrations yet, but they've gone up enough that you can actually measure what has happened. And remember what I said, tropospheric warming, stratospheric cooling, that's what the data is showing from many independent experiments. And the predictions made prediction about temperature change at different latitudes as well. And here, now in the 2000s, you can do predictions in color. And the predictions take into account other effects in addition to greenhouse gases, which dominate in the predictions. The computer models based on physics predict, again, warming in the troposphere, more warming at the poles, cooling upstairs. And you can actually make observations, not over the whole planet, because we don't have a sufficient observation network, but here on the bottom right are the observations actually measured compared with the predictions of the latest computer models. And you can see the observations largely agree. There's warming in the troposphere. The tropopause has gone up a bit, and the cooling in the tropopause and in the stratosphere is occurring. Of course, the predictions aren't perfect. There's a little hole here and a place where some cooling is happening near ground level. Goodness me, call the media, quick. Predictions wrong, shock. Yes, the science still has uncertainties and these models are not perfect. But my feeling is the climate scientists are actually making detailed predictions and they're onto something. Yes, this photograph here has got a carnivore in it. The cat uses 2 kilowatt hours a day if you look at the energy cost of making the grain to feed the animals that the cat then eats. And my estimate, just looking at the energy cost alone, looking at the chemical energy going into the animals that are queuing up, being fattened up in due course to be eaten by the carnivore, the energy cost of running the carnivore in terms of the chemical energy that goes into the animals is about 15 kilowatt hours per day. And then you need to add to that the farming costs, the fertilizer costs, the water costs. So it's bigger than 15 kilowatt hours per day to be a typical omnivore eating, say, 250 grams per day of meat. In contrast, the chemical energy that's actually going in your mouth is only 3 kilowatt hours a day. So you could get by on significantly less. So I agree, there's a good case to be made that switching to a more vegetarian diet can make a big difference to energy consumption. This may not be universally true, because if you have a country where there's lots of grazing terrain, then you can think of the animals as automatic biomass harvesters, which would be difficult to arrange in other ways. So there may be some countries where grazing animals and then eating the animals is a sensible way to harvest the biofuels. Okay, so you're asking about solar flares or possibly sunspots as an explanation of global warming. Is that as a contributor? Okay, I've got some data on this. So This is a graph of what the actual irradiance of the sun has been doing. Presumably, if it's something to do with sunspots, there has to be a mechanism. And the mechanism, I imagine, would have something to do with power coming from the sun to the Earth. So these are measurements of the power of sunshine in watts per square meter over the last 20-some years. And they go up and down as the sunspots go up and down. And I don't see any evidence of something remarkably unusual happening. Of course, we've only got 20 years data, so it's a bit hard to tell. This is what sunspots have been doing since they were recorded, so they go up and down. And this is the correlation between sunspots and solar irradiance. So is there something remarkable going on in the last 20 years? Is there something remarkable? I don't really see anything there. It could be, you could say, oh, this minimum is really unusual compared to other minima. Well, is it? It doesn't look that outstanding to me. And you could say, how do sunspots correlate with temperatures? Well, here's the temperature record, global average temperature, which has been wobbling around and quite probably going up for the last while. And this is what the sunspots were doing in the interim. And I've marked the minima and maxima of sunspots here. And yes, there is a small effect. And through the physics mechanism, going back to this, you can see, you can read off how many watts per square meter it is. It's about 1 watt per square meter at the outside of the planet. Which down at ground level, on average, you divide by 4 and knock a little bit off, it's about 1/4 of a watt per square meter is the effect of sunspots, which goes up and down every 11 years. That is small compared with the effect of increasing CO2, which is in the 1.6 watts per square meter ballpark. So it's a small effect, and I think if you look really, really closely in here, you might be able to see some effect relating to the sunspots, but I don't think it's the explanation of what appears to be a little bit of a temperature rise in recent times. In addition, we do have a mechanism for why we believe CO2 might be having an effect. CO2 is a greenhouse gas. You put it upstairs, it's like adding an extra blanket. It makes it harder for the radiation to get out, and so you expect it to make things warmer downstairs. Okay, that's a great question. Find out how much uranium there is if we get a shortage, and then people have an incentive to explore. If there's more than 40 years of uranium left, then you won't make your money back on exploration. So we really don't know how much uranium there is. The best estimate I've been able to find, given that extreme uncertainty about the uranium resource, is that there might be, say, 27 million tons of uranium that's recoverable. That's including all the unconventional uranium in phosphates as well as the standard mines. Now, this number may well be wrong because we haven't got a shortage yet. But you then ask, okay, how long would that last? And it depends who uses it. And for sake of argument, let's assume that everyone on the planet has the right to nuclear power, not just Britain and America. And let's assume that we want it to last 1,000 years. Then how much power could we get from it? With the little visualization I did there with the 5-fold increase, I was saying you could get 42 kilowatt hours per day per person. Is that doable with 27 million tons of uranium shared between everyone for 1,000 years? The answer is no. You could only get half a kilowatt hour per day per person in once-through reactors, which are the standard non-breeding reactors. So if you want it to be fair, and if you want it to last 1,000 years rather than, say, just 100 years, then you do need to talk about breeder reactors. And with breeder reactors, the whole world could have 1,000 years of uranium-driven electricity to the tune of 33 kilowatt hours per day per person, which is in the same ballpark as what I was showing. So I think the long-term view of nuclear, if humanity decides to go for nuclear in a big way, is that breeder reactors would make a lot of sense, unless enormous discoveries of more uranium are made.